All right, let's go.
Number 12. The four-dimensional world. In 1908, mathematician Hermann Minkowski, building directly on Einstein's 1905 theory of special relativity, gave a lecture that opened with a line still quoted in physics departments today. Space by itself and time by itself are doomed to fade into mere shadows, and only a union of the two will preserve an independent reality. Minkowski's proposal was to stop treating space and time as separate stages and instead treat them as a single, unified, four-dimensional structure, now called spacetime, where every event in the universe's history occupies a fixed coordinate, the way a point on a map occupies a fixed location. This mathematical structure is the foundation of what's now called the block-universe view, or eternalism in philosophical terms. Under this interpretation, the past, present, and future aren't different in kind. They're different regions of the same four-dimensional block, all equally real, the way New York and Los Angeles are both equally real locations, even though you're only standing in one of them right now. Your birth, this exact moment, and your death would all be fixed points within that block, no more capable of being altered than a point on a completed map. This isn't a fringe interpretation layered on top of relativity after the fact. Special relativity's mathematics works the same regardless of whether physicists adopt the block universe view philosophically. But a growing number of physicists and philosophers of physics argue the theory's own internal structure makes the block universe the most natural and possibly the only fully consistent way to interpret what relativity is actually describing. Number 11. The vanishing now. The specific feature of relativity that pushes hardest toward the block universe is the relativity of simultaneity, a direct consequence of Einstein's 1905 postulate that the speed of light is constant for every observer regardless of how fast they are moving. Once that's true, two events that appear simultaneous to one observer can appear to happen at measurably different times to another observer moving at a different velocity. And neither observer is wrong. There's no error being made. There's simply no single universal now that all observers share. In Newtonian physics, before Einstein, this wasn't an issue. Time ticked forward uniformly for the entire universe, and everyone, everywhere, agreed on what counted as the present moment. Special relativity removes that shared present entirely. What counts as happening right now on a planet on the far side of the galaxy genuinely depends on how fast you personally are moving relative to it. A small change in your velocity can shift which events on that distant world currently count as your present, your past, or your future. That single result carries enormous philosophical weight. If there's no objective fact about what's happening now throughout the universe, then singling out the present moment as uniquely real while treating the future as not yet existing becomes very difficult to state in a way that's consistent with the physics. Many physicists and philosophers take this as the central argument for treating all moments as equally real, rather than granting the present some special status the mathematics itself doesn't support. Number 10. The Andromeda Paradox. In 1966, Dutch physicist C.W. Rietvink published an early version of an argument that philosopher Hilary Putnam independently developed and popularized the following year in his paper, Time and Physical Geometry. Their argument uses the relativity of simultaneity directly. If two people are walking past each other on a sidewalk, moving at only a few miles per hour relative to each other, the difference in their reference frames is enough to shift which distant events count as now for each of them by a margin that at galactic distances can amount to days or weeks. Physicist Roger Penrose gave this scenario a vivid illustration in his 1989 book, The Emperor's New Mind, now generally called the Andromeda Paradox. Imagine two people passing each other on the street, one walking slightly toward the Andromeda galaxy, the other walking slightly away. According to relativity's own mathematics, the events that count as now in the Andromeda galaxy for each of these two ordinary pedestrians can differ by several days, meaning that for one of them, a hypothetical Andromedan space fleet has already launched, while for the other, walking the opposite direction on the same sidewalk, the decision to launch hasn't been made yet. The Reitdick-Putnam argument concludes that if both of those launch-related events are equally real relative to two people who are for all practical purposes standing in the same place at the same time, there's no principled way to say one event is real and the other isn't. Both must already be part of a single fixed reality, which is exactly the block universe's central claim. Number 9. Presentism's defense. The philosophical position most directly opposed to the block universe is presentism, the view that only the present moment is real, the past no longer exists, and the future doesn't yet exist. It's also the view that matches ordinary human intuition almost perfectly. Nobody walks around feeling as though their future birthday party is already sitting somewhere, equally real, waiting for them to arrive at it. Defenders of presentism generally take one of two approaches to the relativity of simultaneity problem. Some argue that special relativity is simply incomplete, and that a future, more complete theory of physics will restore some form of preferred, universal reference frame that presentism needs to make sense, a position most working physicists consider unlikely given how thoroughly special relativity's predictions have been experimentally confirmed. Others accept relativity fully, but argue the debate between presentism and eternalism isn't really a physical disagreement at all, that it's a dispute over the meaning of words like real and exists, with no experimental consequence that could ever settle it either way, since both views make exactly the same testable predictions about clocks, light, and measurement. Philosopher Mark Hinchliffe has directly defended presentism against the claim that relativity refutes it, arguing that presentists face real difficulty clearly stating their position using Minkowski's four-dimensional framework, but that difficulty in phrasing a view isn't the same thing as that view being proven false. The dispute, more than half a century after Reitdick and Putnam, remains genuinely unresolved among philosophers of physics. Number 8. The growing block. A compromise position, first proposed by philosopher C.D. Broad in 1923, tries to preserve the intuitive asymmetry between a fixed past and an open future without fully committing to presentism's rejection of the past's reality. Under the growing block universe theory, both the past and the present genuinely exist, occupying real positions in a four-dimensional structure much like the standard block universe describes. The future, however, does not exist yet in any sense. There's no fact of the matter about it at all, because it simply hasn't been added to the block. On this view, the block isn't static and fixed for all time. It's continually growing, with each new present moment adding a fresh, thin slice onto the front edge of an ever-expanding four-dimensional structure, then immediately becoming part of the fixed, unchangeable past that trails behind it. This preserves something the standard eternalist block universe doesn't offer, a genuine, physically real sense in which the future remains open and undetermined, right up until the moment it happens. The growing block theory faces its own direct challenge from the same relativity of simultaneity problem that motivates the standard block universe in the first place. If there's no universal agreed-upon now shared by every observer in the universe, there's no consistent way to define exactly where the growing edge of the block currently sits. Different observers moving at different velocities would disagree about which events have already been added to the block and which haven't, undermining the clean distinction the theory depends on. Number 7. The Quantum Objection. Special relativity is only half the picture modern physics has to reconcile. Quantum mechanics introduces a second independent challenge to the block universe centered on indeterminism rather than simultaneity. In several interpretations of quantum theory, particularly collapse-based models like the GRW theory, developed by physicists Giardi, Rimini, and Weber in 1986, a quantum system genuinely exists in a superposition of multiple possible states, and the specific outcome that occurs upon measurement is not fixed in advance by any prior physical fact. It's fundamentally, objectively random in a way no additional information could ever have predicted beforehand. Philosophers Luca Mariani and Giuliano Tarango have argued this creates a real problem for eternalism, developing the concept of a strong indeterminate present. Right up until a quantum collapse event actually occurs, there may be no fact of the matter about which outcome will happen, meaning that specific future event genuinely isn't sitting in the block yet, waiting to be reached, the way the standard eternalist picture requires. Once the collapse happens, it becomes fixed and enters the block permanently. But beforehand, under this argument, it may not exist in any determinate form at all. This objection specifically targets collapse-based interpretations of quantum mechanics, not quantum theory as a whole. Whether it succeeds in genuinely threatening the block universe view, or whether it only threatens one particular family of quantum interpretations while leaving others untouched, remains an active and unresolved debate. Number 6. The many worlds escape. The quantum objection loses much of its force under a different, equally mainstream interpretation of quantum mechanics, the many worlds interpretation, developed by physicist Hugh Everett in 1957. Under many worlds, there is no random collapse of the wave function at all. Every possible outcome of every quantum event occurs, with reality branching into separate, equally real timelines for each one, meaning the underlying evolution of the universe's total wave function encompassing every branch remains completely deterministic and smoothly continuous the entire time, with nothing genuinely random or objectively undetermined ever actually happening at the fundamental level. Physicists sympathetic to the block universe view have pointed out that many worlds effectively neutralizes the quantum objection by removing indeterminism from physics altogether, at the cost of accepting a vastly larger, branching structure of reality. Under this combined view, the universe's total wave function, encompassing every branch, forms its own kind of fully determined four-dimensional block, just one dramatically larger and stranger than the single timeline Minkowski originally had in mind, since it would need to include every branch, not just the single one we happen to be experiencing. This doesn't resolve the underlying disagreement so much as relocate it. Instead of debating whether the future already exists within a single timeline, the question becomes whether every possible future already exists across every branch, which is either a more elegant solution to the tension between relativity and quantum mechanics, or a significantly larger metaphysical commitment, depending entirely on which physicist or philosopher you ask. Number 5. The Entropy Arrow. If the block universe is correct and every moment is equally real, an obvious question follows: why does time feel like it moves in only one direction? Why do we remember the past clearly but have no memory of the future at all? And why does an egg splatter on the floor but never reassemble itself back onto the counter? The most widely accepted physical answer traces back to the 19th century work of physicist Ludwig Boltzmann on statistical mechanics, and was given its now standard name, the Arrow of Time, by astronomer Arthur Eddington in 1927. The underlying physics is almost entirely about probability, rather than any fundamental asymmetry in time itself. Nearly all of the basic laws of physics, including Newton's laws, Maxwell's equations, and the core equations of quantum mechanics, work identically whether time runs forward or backward. An egg splattering and an egg unsplattering are both, in principle, equally valid solutions to the underlying microscopic equations. What actually creates the felt direction of time is entropy. The number of possible disordered arrangements of matter vastly outnumbers the number of ordered ones, so systems overwhelmingly tend to evolve from lower entropy, more ordered states towards higher entropy, more disordered ones, simply because there are astronomically more ways to be disordered than there are to be ordered. Under the block universe view, this doesn't require time to genuinely flow in one direction at all. The entire four-dimensional block can simply have lower entropy at one end and higher entropy at the other, permanently and statically, the same way a book can have its story arranged in order from first page to last, without the book itself needing to be doing anything. Our subjective sense that time is passing, on this account, isn't physics happening, it's a specific local consequence of living inside the higher entropy end of an already completed structure. Number 4. The timeless equation. Attempts to combine general relativity with quantum mechanics into a single theory of quantum gravity run into a problem that makes the block universe debate look comparatively mild. The Wheeler-DeWitt equation, developed by physicists Bryce DeWitt and John Wheeler in the late 1960s as a leading candidate equation for the wave function of the entire universe, contains no explicit time variable at all. Applied to the universe as a whole, the equation appears to describe something genuinely static, a single frozen configuration with no variable representing change or evolution built into the mathematics whatsoever. This is known in physics as the problem of time and quantum gravity, and it remains formally unresolved across every major approach to quantizing gravity, including loop quantum gravity. Physicist Julian Barber has taken the most radical position on what this might mean, arguing across decades of work that time may not be a fundamental feature of reality at all, that the universe should instead be understood as a fixed, timeless collection of possible three-dimensional configurations, a landscape he calls Platonia, with our experience of moving through time emerging only as an approximate local illusion generated from within one particular configuration. Where the ordinary block universe still preserves time as a genuine fourth dimension laid out within the block, Barber's Wheeler-DeWitt-based picture goes further, suggesting that even the block itself might be the wrong metaphor, that what's fundamental isn't a four-dimensional structure containing time, but a structure that doesn't require time as an ingredient at all. Number 3. The relational present. Not every physicist working on quantum gravity has followed Barber toward a fully timeless universe. Physicist Carlo Rovelli, a co-founder of Loop Quantum Gravity, has argued in the opposite direction across several books, most prominently The Order of Time in 2018, that physics has been too quick to eliminate time and becoming from its fundamental picture of reality, and that what genuinely doesn't exist at the fundamental level isn't time itself, but a single, universal, observer-independent time shared by the whole universe at once, precisely the kind of time Newton assumed and relativity ruled out. Rovelli's relational view holds that time and change are always relative to a specific physical system and its interactions with other systems, never a single global backdrop the entire universe shares. Under this framework, there's no single fact about now for the universe as a whole, which agrees with standard relativity, but Rovelli argues this doesn't mean genuine becoming and change are illusions requiring a static block to explain them away. It means our instinct to imagine one single shared present moment for the entire cosmos was always a Newtonian assumption relativity had already quietly dismantled well before questions about the block universe ever entered the picture. This puts Rovelli in a genuinely distinct position from both strict eternalists and traditional presentists. He accepts nearly everything relativity says about the absence of a universal now, while still resisting the conclusion that physics is committed to a single, frozen, block-shaped universe where nothing is actually happening. Number 2. The free will question. If the block universe view is correct and the future already exists as fixed as the past, a genuinely uncomfortable philosophical consequence follows directly from it. Physicist Veselin Petkov has stated this implication in stark terms. In a four-dimensional Minkowski world, there is no free will, because the entire history of every object, including every choice a person will ever make, is already fully realized as a complete, unchanging structure, existing all at once rather than being generated moment by moment through anything resembling a decision. Not every philosopher who accepts the block universe accepts this conclusion, however. Philosopher Joseph Berkowitz has argued for a more limited reading. The block universe rules out any literal ability to change the future, since the future is already fixed and unchangeable in exactly the same sense the past is. But he distinguishes this from the impossibility of influencing what the future turns out to be. Your choices on this account aren't causally irrelevant just because the outcome they produced was always going to be part of the block. They're simply part of the fixed causal chain that determined, from the beginning, exactly which future was ever going to exist in the first place. This distinction between changing a fixed future and being a genuine, necessary part of how that fixed future came to be the one that exists is where most of the serious philosophical work on the block universe and free will currently sits, without anything resembling a settled consensus on which side is correct. Number 1. What physics actually settles. Special relativity's own mathematics does not require anyone to adopt the block universe view to use the theory correctly, make its predictions, or build a GPS satellite with it. What relativity of simultaneity does establish without much serious dispute among physicists is that there is no single universal observer-independent present moment shared with the whole universe, a result confirmed daily by the same equations that keep every GPS satellite synchronized. Everything built on top of that fact, from the Reed-Dike-Putnam argument to the growing block theory to Ravelli's relational becoming, is an interpretation of what that missing universal now actually implies about what's real. Quantum mechanics complicates the picture rather than resolving it. Depending entirely on which interpretation of quantum theory turns out to be correct, a question physics itself has not settled after nearly a century of experiments. Either the future remains genuinely objectively open in a way no version of the block universe can fully accommodate, or it's already fully determined across every branch of an almost incomprehensibly larger structure than Minkowski ever proposed. And the deepest attempts to unify relativity with quantum mechanics into a single theory of gravity don't clearly settle the dispute either. They mostly reveal that physicists don't yet have full agreement on what time is doing in the fundamental equations at all. What can honestly be said is this: nothing in confirmed experimentally tested physics rules out the block universe. Nothing in confirmed experimentally tested physics proves it either. The question of whether tomorrow already exists remains open specifically because relativity and quantum mechanics, physics's two most successful theories, have never been fully reconciled, and until they are, the future's reality or unreality depends on which of two theories anyone chooses to take more seriously. 12 arguments, and none of them close the case. Minkowski's four-dimensional spacetime and the relativity of simultaneity push hard toward treating tomorrow as already real. Quantum indeterminism, the felt asymmetry of entropy, and the unresolved problem of time in quantum gravity all complicate that picture in different, sometimes contradictory directions. Physics has spent over a century building the tools to ask whether the future already exists. It has not yet built the tools to answer it. Subscribe to Cosmic Hives. See you in the next one.